Energy is the capacity to do work. Here are some common forms of energy: radiant energy, thermal energy, chemical energy, nuclear energy, and potential energy. We will concentrate in this chapter on thermal energy, the energy associated with the motion of molecules and atoms; chemical energy, the energy stored within the bonds of chemical substances. Energy changes in chemical reactions. Heat is the transfer of thermal energy between two bodies that are at different temperatures. Temperature is the measure of thermal energy, but remember that temperature is not equal to thermal energy. Thermochemistry is the study of heat change in chemical reactions. The system is the specific part of the universe that is studied. Here are three systems: an open system, which exchanges both mass and energy; a closed system that exchanges only energy; and an isolated system that does not exchange anything. An exothermic process is any process that gives off heat. It transfers thermal energy from the system to the surroundings. Hydrogen reacting with oxygen to generate water releases energy. Water vapor becoming water liquid through condensation releases energy. An endothermic process is any process in which the heat has to be supplied to the system from the surroundings. In order to convert mercuric oxide into mercury and oxygen, energy must be supplied. Energy must be supplied to melt solid water, ice, into liquid water. Remember that an exothermic system, heat is given off by the system to the surroundings, where in an endothermic process, heat is absorbed by the system from the surroundings. Thermodynamics is the scientific study of the interconversion of heat and other kinds of energy. State functions are properties that are determined by the state of the system, regardless of how that condition was achieved. Look at the diagram. There are two hikers that took different paths. However, their potential energy is the same. It only depends on where they started and where they ended up. Energy, pressure, volume, and temperature are all state functions. These formulas show you that to calculate the change in internal energy, delta U, you have to know the difference between the final and initial energies. Same is true for delta P, delta V, and delta T. The first law of thermodynamics: energy can be converted from one form to another, but cannot be created or destroyed. It is the conservation of energy. The internal energy of a system, the change in the internal energy of the system, plus the change in the internal energy of the surroundings equals 0. Or, the change in internal energy of the system equals the negative of the change in internal energy of the surroundings. Here propane is burned with oxygen to generate carbon dioxide and water. It's an exothermic chemical reaction. The chemical energy lost by combustion equals the energy gained by the surroundings. Another form of the first law for the change of the internal energy of the system is that the change in internal energy equals Q plus W. Q is the heat exchange between the system and the surroundings. W is the work done on or by the system. W equals the negative of the external pressure P times the change in volume when a gas expands against a constant external pressure. Here are sign conventions for both work and heat. Enthalpy and the first law of thermodynamics. The first law again is delta U equals Q plus W. The internal energy equals the heat plus the work. At constant pressure, however, Q, the heat, is equal to delta H, the change in enthalpy. And W, the work, equals the external pressure minus P times the change in volume. Look at the diagrams. Here the volume changes, and it's delta V. Delta U then is equal to delta H minus P delta V. Remember, this is only true at constant pressure. Delta H equals delta U plus P delta V. The enthalpy equals the internal energy times plus the pressure times any change in volume.